this lecture we consider classical scheduling algorithms for aperiodic system. For aperiodic scheduling, we first consider scheduling with no precedence constraints. So we don't have any given dependencies between tasks that define if one task has to be executed before or after another. So here we define the set of TIs to be a set of tasks, and we define certain parameters for this. We define the parameter CI to be the execution time of a given task TI. We define the parameter DI to be the deadline interval, which is the time between the point in time when the task becomes available and the point in time when the task has to finish its execution in order to keep its deadline. When we have DI and CI defined, we can also define LI, the so-called laxity or slack time, which is simply the deadline of the task minus the execution time of the task. So the amount of spare time we have when executing our task. And the last parameter we define is the finishing time, FI, which is simply the time when the task is finished. On a single processor time, with equal arrival times, so when all tasks arrive at the same time, preemption is useless because, yeah, we have all processes or all tasks arriving at the same time, so no task arrives later and will interrupt the other ones. So a simple scheduling algorithm here is a so-called earliest due date algorithm, or EDD, and this simply defines that the processor should execute the task with its earliest due date or earliest deadline first. So here we have given 3 tasks, and the green, yellow, and purple amount of time are actually the execution times, and the complete length of the bar defines the deadline for these tasks. And now we start assigning the tasks according to the earliest deadline. So the earliest deadline is the green task here, so we add it first, and we see we have the finishing time of this task defined here. Then the second next deadline is the purple task here, so we assign it as a second task and have the finishing time here. And finally, the task with the latest deadline is the yellow task, so we schedule this one last. So EDD requires that all tasks are sorted by their absolute deadline. So EDD has a complexity of O of n log n. So we can actually prove that EDD is an optimal scheduling approach for this problem, since it follows so-called Jackson's rule. And Jackson's rule describes that if we are given a set of some n independent tasks, any algorithm that executes these given tasks in order of non-decreasing absolute deadlines is optimal with respect to minimizing the maximum lateness. And the proof has been given by Butazzo in 2002, and this starts off with a schedule. So let us assume we have a schedule tau, which is produced by any algorithm A, so it just defines any order to execute tasks. Now we check if A is not the EDD schedule, then we know that there exists 2 tasks, TA and TB, with deadlines dA less or equal than deadline of B, and for which task B immediately precedes task A in our schedule. And now let us assume we simply exchange both tasks A and B in the schedule, and let T prime be that new schedule that we obtain by exchanging these 2 tasks. So we start off with this schedule tau here, and we have these 2 tasks TB and TA, and we simply exchange them, so TA comes before TB. Now we want to show that exchanging both tasks TA and TB in our schedule cannot increase the lateness. So the maximum lateness for the 2 tasks TA and TB in the schedule tau is Lmax of AB, is the finishing time of A minus the deadline of A. Now, if we consider the schedule T prime, where TA and TB are actually switched here, we know that the maximum lateness for TA and TB in this T prime schedule is the maximum of the latenesses of A and B for the new schedule. Now we have 2 possible cases here. On the one hand, the lateness of A in this new schedule might be larger or equal than the latency of B in the new schedule. Now from that follows that the lateness of both tasks equals to the finishing time of A in this new schedule minus the deadline of A. And this is less than the finishing time of A in the original schedule, since we moved A in front of here, minus the deadline of A, which is the maximum lateness of AB. On the other hand, it might be the case that the new lateness of A is less or equal than the new lateness of B. So this implies that the maximum lateness for A and B under the new schedule is the finishing time of B under the new schedule minus the deadline of B, which is the finishing time of A in the original schedule minus the deadline of B. And this again is less or equal than the finishing time of A in the original schedule minus the deadline of A, which again is the maximum lateness of AB in the original schedule. And this is the case since the finishing time of A is the finishing time of B in the new schedule, and the deadline of A is less than or equal the deadline of B. And from this follows that the new maximum lateness in the new schedule for A and B is less or equal than the maximum lateness in the original schedule for A and B. And so we have proven that exchanging both tasks TA and TB in this schedule here will not improve the lateness here, increase the lateness here. Now then we can show that EDD is optimal, because any schedule tau with a lateness L can be transformed in some EDD schedule Tn with some lateness Ln, which is less or equal than L, the original lateness, which is the minimum lateness. And so if we perform all these steps, we get an optimal schedule, and so we know EDD is optimal, and we have proven this. Now, when we have a system where tasks can arrive at different times, we can actually use preemption to potentially reduce the lateness. So here we consider now a different scheduling algorithm, the so-called earliest deadline first algorithm, or EDF, and we start off by discussing Horn's theorem. So that theorem, stated in 1974, states that if we are given a set of n independent tasks, and these tasks have arbitrary arrival times, any algorithms that at any instant executes the one task with the earliest absolute deadline of all the ready tasks is an optimal algorithm with respect to minimizing the maximum lateness. What does this mean for this algorithm? The earliest deadline first algorithm performs action each time that a new task that is ready to execute arrives. This task is inserted into a queue of ready tasks sorted by their absolute deadline, as you see on the bottom of the slide here. There's a task that's executing, and it's at the head of the queue where there's only one task at that moment, so it's executed. And then new tasks arrive. So we have one task that arrives, another one with a larger absolute deadline, and possibly a third one. And now a newly arrived task actually comes, which has a deadline which is less than the deadline of the task that's currently executing. So this executing task is actually preempted, it's taken away from the CPU, and that newly arrived task is now put on top of the queue and is executing. So this is a straightforward approach if you implement it with sorted list, but you have to do a full comparison here with existing tasks for each task that arrives, and this would require a runtime of O of n square. You can actually optimize this if you perform this sorting or searching with binary search or bucket arrays here. Now let's consider an example for earliest deadline first. We have given 3 tasks, T1, T2, and T3, with different arrival times, duration, and deadlines. So T1 is ready at time 0 here, T2 is ready at time 4, and T3 is ready at time 5. All tasks take a different time to execute, so T1 uses 10 units of time, T2 only uses up 3 units of time, and T3 again needs 10 units of time. And all the tasks have different deadlines. So T1 has to be finished at time 33, T2 has to be finished earlier at time 28, and T3 again has to be finished a bit later at time 29. So at time 0 there is one task arriving, there is no other task, so T1 can start off and start executing, and it executes until the point in time when the next task is ready, which is time 4 when T2 arrives. Now we see earliest deadline first. We check if the deadline of the newly arrived task is actually less than the deadline of the task that's currently executing, and this is the case here. 28 is of course less than 33, so T1 is preempted and T2 starts executing here. So how long does it start executing? Well, for each step in time, actually we have to reconsider it. So here T2 starts off, executes for one time unit, then T3 arrives. T3 has a deadline of 29, T2 has a deadline of 28, so T2 can actually continue executing, and it can continue executing until time 7. Now what happens at time 7? At time 7, T2 has executed 1, 2, 3 time units, so it's actually finished here. So it's finished, T3 is finished, so the waiting task T3 can now actually take over because it has the smallest deadline of the remaining tasks. So finally at time 7 T3 is started, and T3 now executes for 10 units until it's finished, and when T2 is finished here, T1 again can take over and execute until itself is finished. Now again we want to show that EDF is an optimal scheduling algorithm, so we want to show that EDF minimizes the maximum lateness. And the proof again was performed by Butazzo 10 years ago. And we start off by some definitions. We define tau to be a schedule that is produced by some generic schedule A. And we have a tau EDF schedule, which is a schedule that would be produced by an EDF scheduler. And we know that we want to allow preemption, so preemption means that tasks are executed or can be executed in disjoint time intervals, so there can be an interruption between the time two parts of a task execute. Now the schedule tau is divided in time slices of one time unit each, and we denote the time slices by an interval which is inclusive of t and exclusive of the time unit t plus 1. Now we define tau of t to be the task executing in that interval t, starting at point in time t and extending until just before t plus 1. And we define E of t to be the task which has the earliest deadline at the point in time t. Now, the time te of t is the point in time which is larger or equal than the point in time t, at which the next slice of some task et begins its execution in the current schedule. Now, if the schedule we are considering is not equal to earliest deadline first, then we know that there is a point in time t at which the schedule, the process that is scheduled in this original schedule, is not the process with the earliest deadline. So the idea again here is that if we swap these tasks tau of t and E of t, we cannot increase the maximum lateness. So let's consider the example here. At this red line we have tau of t is 3, E of t is 2, we have te of 5, and we have a schedule of te of 2. And when we swap this here, we see we do not increase the maximum lateness of the system. Now if we have a schedule tau of t that starts at t equals 0, and we have a maximum deadline capital D, which is a maximum of all the deadlines in the system, then we can obtain the EDF schedule from the original schedule that was given, the tau schedule, by using at most capital D transpositions here. And there is an algorithm for this, the interchange algorithm. this starts at point in time t to d minus 1, so to the point in time before the latest deadline. And now it checks if the task scheduled at this point of t is equal or not equal to the task with the earliest deadline. And if it's so, it just exchanges the both tasks. And so using the same algorithm as before with the earliest due date, like we've seen in the proof of Jackson's algorithm, we can easily show that swapping cannot increase the maximum lateness. And for this case, for this reason, EDF is optimal here. Now, does interchange preserve schedulability? Now, on the one hand, we consider the case that the task with the earliest deadline is moved ahead. So, if we have been able to keep the deadline in the original schedule, we can ensure to meet the deadline in that new schedule already, because we already kept the deadline before. On the other hand, if we delay a given task at that point in time, if the schedule for that task is feasible, then we know that the point in time where this task with the earliest deadline was executed, plus 1, is still less or equal than the deadline of that task, which is the earliest deadline. Now we know from the definition that this earliest deadline is of course less or equal than any other deadline. So we know that TE plus 1 is less than or equal than any other deadline DI. And this guarantees that the delayed task is also schedulable. Let us consider a third scheduling algorithm, the so-called least laxity or least slack time first algorithm. This algorithm assigns priorities to tasks, and these priorities are a decreasing function of the laxity of the task. So the lower the laxity of a task is, the higher priority it gets. This algorithm is changing the priority of tasks dynamically, and it's preemptive. So we are given the same set of tasks as in the example for EDF before, and now let us see how least laxity actually handles this. Now, as before, at the point in time 0, we start T1. T1 arrives, nothing else is running on the processor, so it can run until time 4. At time 4, T2 arrives, and now at this point in time, we have to check the laxities of both of these tasks here. So we calculate the laxity of T1, which is 33, its deadline, minus the already executed units in time, 4, minus the rest of the units in time it has to execute, 6, since its complete duration is 10 units in time. So the laxity of T1 is 33, minus 4 already executed units in time, minus 6 time units still to execute is 23. And again, we check this for the second newly arrived task, and we know its deadline is 28. We've already have 4 time units passed where T2 wasn't able to execute anything, so minus 4. And it still has all of its time to execute. It has 3 time units to execute, so its laxity is 28 minus 4 minus 3 is 21. So 21 is of course less than 23, so now we change priorities, and as a consequence T2 is now scheduled, and in the next time unit, time 5, T3 arrives and is ready to execute. And now again we have to recalculate all the laxities here, now for all of the 3 tasks. So for T1 it's easy, 1 more time unit has passed, it didn't proceed any calculations, so it goes down from 23 to 22. For T2, 1 more time unit has passed, but 1 unit has also been executed, so its laxity stays at 21. And for the newly arrived task T3, this has a deadline of 29. 5 units in time have already passed, and it still has all of its calculation time to perform, so 10 units to execute. So the laxity for T3 now is 14. And while T3 is calculating here, is working on the processor, of course, the laxities for all the other tasks are continually decreasing, so they are just waiting for the processor. They cannot perform any calculations because T3 is using the processing time. And finally, at a point in time 13, there is a point when the laxity of T1 is reduced to 14. The laxity of T3 is still 14 because it continues executing one time unit with each decreasing time unit. And now the laxity of T2 has decreased as far as 13. So now again, we are rescheduling the processor to the task with the least laxity here. So T2 is executing, and again, we check now what's happening, and T2 can now execute its 2 remaining time units, and then it's finished. So when T2 is finished, we only have T1 and T3 left, so we recalculate the laxities here for T1 and T3. Now in this case, the laxities for T1 and T3 are equal. They are both 12, so we choose one of these tasks, in this case T3. Now in this case, after one time unit, the laxity of T1 has reduced to 11, while the laxity of T3 is 12 still. So we switch over to T1, and again we switch over some time units later. So what are the properties of the least laxity algorithm? It's not sufficient to call the scheduler, as we've seen, and recompute the laxity just at the times when a task arrives, because the laxities change at every time unit in our system. So with every tick of our clock, we have to recalculate all the laxities. We have overheads for calls of the scheduler, and we may have many context switches. What's interesting is that least laxity schedule can detect missed deadlines early, and least laxity is also an optimal scheduling for single processor systems. However, there is one thing to consider. Since least laxity uses dynamic properties, we cannot use it with a fixed priority operating system, and least laxity scheduling requires, like the scheduling approach before EDF, the knowledge of the execution time of a task. So now let us consider scheduling without preemption. So let's start off with a lemma. If we do not allow preemption in a system, optimal schedules may have to leave a processor idle at certain times. Let's try to prove this lemma. Let's suppose optimal schedulers never leave the processor idle. So we construct an example. We have a task T1, which is periodic, and the calculation time, the execution time of this task T1 is 2. The period of this task is 4 time units, and the deadline of this task is also 4. We have a asynchronous task, which is occasionally available. This is task T2, and this is occasionally available at times 4 times n plus 1, with an execution time of 1 time unit, and a deadline which is also 1 time unit. And we define that the first task here, the periodic task, has to start at T0. Now what happens here? At time 0, T1 gets available, and it starts off. It executes for 2 time units. While it's executing, it cannot be preempted, since we're considering scheduling without preemption here. And at the time 0 times 4 plus 1, so at time 1, T2 comes available here, but it cannot preempt T1, so T1 continues executing. So at the time when we are able to switch to T2, the deadline for T2 is already missed. So it can execute here, but again we missed the deadline, so we have no chance. On the other way around, if we leave the processor idle here, we can execute T2 first, leaving the processor idle for 1 time unit. It arrives at a point in time 5, and then we schedule T2 afterwards, and both deadlines are kept. So we see in that first case here we miss the deadline, but on the other hand we see that there is a possible schedule of starting T2 first. So the schedule is not optimal. It leaves an empty slot here, the time between 4 and 5 in the processor, and thus we have a contradiction. So we proved our original assumption that optimal schedules may have to leave the processor idle at certain times if we do not allow preemption here. So for optimal scheduling algorithms, we need knowledge about the future. So again, no online algorithm can actually decide whether or not to keep a processor idle. Among all of the scheduling algorithms that are not keeping the processor idle at certain times, EDF is optimal. However, if arrival times are known a priori, the scheduling problem becomes, in general, NP-hard. Here, typically, some approach like branch and bound is used. As today's lecture, we have defined mapping terms, we have defined terms for resource allocation, assignment, binding, and scheduling from high-level synthesis. We have seen several kinds of deadlines. We know what hard and soft deadlines are. We are considering hard deadlines here. We considered several approaches to scheduling, static versus dynamic scheduling, and here we have the relation to time-triggered operating systems, and we have seen what a schedulability analysis is and what it can do for us. In scheduling approaches, we have considered classical scheduling for aperiodic tasks with no precedence relations. We have considered approaches for simultaneously starting tasks, the EDD approach, and also approaches for asynchronous arrival times like EDF and least laxity. So this concludes today's lectures. Thanks for listening. Until next time. Thank you.